Welcome to Durham and welcome to the Department of Computer Science. Today I would like to give you an impression of what it is like to study the MSc in Scientific Computing and Data Analysis, or MiSCADA for short, here in Durham. I'm Dr. Anne Reinartz. I'm the director of MiSCADA. MiSCADA is a course made by scientists for the next generation of scientists. Our courses focus on building an understanding of the algorithms and software tools that have become ubiquitous in modern science. The course instruction is structured into two parts. Every student takes MiSCADA's methods training, where you learn how to write large-scale scientific simulations and how to analyze large quantities of very complex data. But methods shouldn't remain abstract, so each MiSCADA student has a specialization area, a domain to which these core skills are applied. The specializations we currently offer are financial technology, earth and environmental sciences, astrophysics, computer vision and robotics, AI infrastructure platforms, and AI for engineering. The components every student takes in Term 1 are scientific computing, high-performance computing, introductory statistics and machine learning, and professional skills. In Term 2, students have a choice of optional modules, such as Advanced Statistical and Machine Learning, Foundations and Unsupervised Learning, Advanced Statistics and Machine Learning, Regression and Classification, Performance Modeling, Vectorization and GPU Programming, Data Acquisition and Image Processing, Advanced Algorithms and Discrete Systems, and Computational Linear Algebra and Continuous Systems. As you can see, not all optional modules are available to all streams. Finally, in Term 3, you will have the opportunity to work closely with an academic on a research project, which will form your dissertation. For now, let's have a look at what one of your core lectures might look like. In particular, let's take a look at financial mathematics with Dr. Chunrong Feng.
Hello everyone, my name is Chunrong Feng from Department of Mathematical Sciences. I'm the module leader of Financial Mathematics, and I'm very pleased to provide you with a brief overview. Through MiSCADA's Financial Mathematics specializations, students will be introduced to the mathematical principles behind the modern financial markets. Financial mathematics draws on tools from probability theory, statistics, partial differential equations, and scientific computing, and is widely used in investment banks, hedge funds, insurance companies, cooperative treasuries, and regulatory agencies to solve such problems as derivative pricing, portfolio selection, and risk management. The financial mathematics specialization has a very strong mathematical flavor and educates students who will later work within quantitative divisions of fintech companies. This module introduces fundamental ideas of mathematical finance, such as financial derivatives and markets, self-financing portfolios, and arbitrage-free pricing. These ideas will be used to price financial products in both discrete time and continuous time markets, using both theoretical and computational approaches, such as Monte Carlo or other numerical methods. The theory includes an introduction to the tools of stochastic calculus and other essential ideas from probability theory, such as martingales. The computational aspect involves implementing numerical methods using Python. Now I will use a simple model to illustrate how mathematics is applied in finance. One fundamental assumption in finance is the concept of no arbitrage opportunities. A model is considered flawed if it allows investors to make a profit without any risk of loss. Such scenarios are termed arbitrage opportunities. But how can we describe this concept mathematically? In fact, there's a well-known theorem stating that there are no arbitrage opportunities if and only if there exists a martingale probability measure. So what is a martingale measure, and how do we calculate it? I would like to use a simple example to demonstrate how to determine. Let's consider a two-period model with one stock. For simplicity, we assume the interest rate is 0. At time 0, the price of the stock is £4. At time 1, the price may either go up to £6 or go down to £2. At time 2, the price will change again. Regardless of the real-world probabilities for these changes, we can calculate the martingale measure. Since we assume the interest rate is 0, we don't need to discount the price. Now let's look at the period from time 0 to time 1. We will calculate the probabilities using the following method. We take the expectation of the price at time 1 and this probability and set it equal to the price at time 0. In other words, we calculate 6 times P plus 2 times 1 minus P equals to 4, where P is the probability of the price going up to £6. And the sum of the probability must be 1. Solving this, we find P equals to half, so the probabilities are half and half. Similarly, from time 1 to time 2, we calculate the probabilities. 8 times 1/3 plus 5 times 2/3 equals to 6 for the price going up, and 4 times 1/3 plus 1 times 2/3 equals to 2 for the price going down. Now we take the product of these probabilities to get the martingale measure. For example, for omega 1, the martingale measure is half times 1/3. We will get this 1/6, and so on. So what is financial mathematics? Financial markets are very complex systems that are inherently random. Quantities such as stock prices, interest rates, etc., they are naturally modeled as stochastic processes. A common approach is to represent them using geometric Brownian motion, as in the Black-Scholes model, which is a solution of a linear stochastic differential equation. The basic mathematics needed here is stochastic calculus and measure theory, including Edel's formula, martingale theory, etc. Financial products such as options are contracts that can be traded and may entitle the holder to specific payoffs if certain conditions are met over a defined period. Pricing these options is a critical task in financial mathematics. The fundamental concept of arbitrage leads to a consistent pricing mechanism, but demands some advanced probability theory, including martingales and change of measure techniques. Now let's examine a graph depicting ExxonMobil's stock price data over 5 years. The curve appears continuous, yet exhibits significant fluctuations, which is typical because stock prices are inherently random. Next, consider a graph of Brownian motion, which can be approximated by a random walk. The path of Brownian motion also appears highly erratic. How irregular is it? In fact, studies in stochastic calculus reveal that the paths of Brownian motion are continuous, but nowhere differentiable. Just as we can construct discrete models based on the random walk, we can derive various continuous models by employing Brownian motion as a fundamental source of randomness. This derivation is accomplished through stochastic differential equations. For instance, the renowned Black-Scholes model characterizes the stock price process using an SDE that represents geometric Brownian motion. Solving ordinary differential equation is manageable with elementary calculus. However, SDEs present greater challenges due to the inclusion of terms like dWt, where Wt denotes a Brownian motion, which is continuous but nowhere differentiable. A remarkable achievement of stochastic calculus is its ability to provide a coherent framework for interpreting and solving SDEs of this nature. To comprehend the Black-Scholes model and other similar models, it is essential to understand and apply the principles of stochastic calculus. The structure of the module is as follows. Term 1 comprises blocks 1 and 2, covering probability background and discrete time financial markets. Term 2 consists of block 3, which focuses on continuous time financial markets, and block 4, which addresses computational methods. Thank you very much for watching. I'm looking forward to seeing you in the program.